It certainly entered my vocabulary. So. We were discussing very different things. I think it got really too excited.
How do I get rid of this? Do you know? Yeah, but it doesn't work. Oh, it doesn't. See, I cannot click on it.
Maybe you have to switch to the
I'm gonna unplug this for a second. Let me see if I can.
yeah, exactly.
Okay. Oh, now it will stop sharing that too. Okay. Okay, great.
Yes, we have a pretty good crowd. So are you ready?
Okay, yeah.
Okay, so welcome everyone to this week's quantum theory seminar. And it's a pleasure to have our speaker be present here in person. So those of you who have been around here for a while probably remember the last time Ryan gave one of these, but it was virtual. So Ryan is actually my academic younger brother. He got his PhD with Superior Research Lab at Harvard, and then moved on to a postdoc as a Princeton Quantum Initiative Fellow 3 years ago. And well, Ryan has been one of the early pioneers of doing theory for these Rydberg atom simulators, but he's actually very versatile. So he's also worked on array systems and all kinds of other things. And just yesterday, I found out that he was such an incredible PA at Harvard that he was appointed the pedagogy fellow by the Bach Center for Teaching and Learning. So which means we have a treat ahead of us. So yeah, welcome.
So thank you, Devendra, for the very nice introduction and for having me here. I don't know if I can live up to the hype, but I'm certainly very excited to tell you about some recent work we've been doing on understanding the non-equilibrium dynamics of large quantum systems. So understanding the dynamics out of equilibrium for a large quantum system is by and large a very challenging problem. We have good methods to understand the dynamics of small systems at late times, namely exact diagonalization. We can understand the dynamics of large systems for short times with tensor networks, but large systems at late times is where sort of the problem lies. Okay? So one sort of vision to address this challenge is Feynman's idea of quantum simulation. So quantum simulation, as many of you probably know, refers to the philosophy that if you have a quantum system that's difficult to solve analytically or numerically, you just use another quantum system, which is simpler, to emulate the physics. Okay? So this is also what Feynman was talking about nearly 40 years ago. It's just that today we have a lot of better devices to actually implement this, right? So in fact, there are many platforms that we can use today for quantum simulation and to study dynamics. I list here a few, like superconducting qubits, ultra-cold quantum gases, neutral atom arrays, and quantum dots. These are just some of the platforms that I have personally worked on. There are many others, like trapped ions, that I haven't listed here. So the choices are quite varied. So for the purposes of today's talk, the theory and the experiments that I'm going to be showing you are on neutral atom arrays, but this work is completely general. So, you can think about this in the context of superconducting qubits or your favorite platform. This is really platform agnostic and not tied to any specific quantum hardware. Okay. All right, so before going ahead, let me just take a minute to acknowledge my collaborators. So all the theory work that I show you today was done in collaboration with David Hughes at Princeton. And all the experiments were done in Misha Lukin's group, led by Tom, Sophie, and Seppa. So the platform we are going to be looking at today, Rydberg atom arrays. Many of you in the room have heard a lot about this platform. but in case you haven't, I just want to give you a quick overview of the system. So what we have are a bunch of atoms that are trapped in optical tweezers. So optical tweezers are tightly focused laser beams, and these atoms are trapped here. And each atom, at least for a theorist's purpose, can be in one of two states. They can either be in their atomic ground state, or they can be in a very highly excited Rydberg state, which has a large principal quantum number. And although this is a relatively new technology compared to, say, superconducting circuits, over the last decade or so, these have turned into incredibly versatile platforms for quantum simulation of exotic phases of matter, phase transitions, and quantum dynamics. Okay, in order to make further progress, let's start by looking at the very microscopic physics of these atoms in tweezers. So two atoms which are excited to the Rydberg state, they actually interact very strongly with each other via this dipole-dipole interaction, which causes 1 over r to the 6th. Okay. So in the system, there's usually a laser driving these atoms. That laser has a characteristic Rabi frequency omega, and that drives transitions between the ground and the Rydberg state. So that's this Rabi flipping between the ground and the Rydberg state is just the physics of one Rydberg atom. But what's interesting is if you have more than one, right? So for instance, if you just consider two atoms, the state where both of the atoms are in the Rydberg state, this RR state, you can see that because of this van der Waals interaction, which is really strong, this RR state gets driven out of resonance. So the laser can no longer drive transitions to this state where both of the atoms are in the Rydberg state. And that is what we call the Rydberg blockade. So the Rydberg blockade refers to the idea that if one atom is excited to the Rydberg state, that prohibits the simultaneous excitation of nearby atoms in some characteristic blockade radius to the Rydberg state. Okay. So pictorially, for instance, say this dark red atoms are in the Rydberg state. We define a blockade radius marked by this pink circle. And within this pink circle, a second atom cannot be excited to the Rydberg state. And you can immediately see that because of this blockade physics, you can have a strongly correlated system. All right. So we've talked about one particle, two particles, and now naturally we go to many particles. Okay. So if you want to write down a many-body Hamiltonian for the system, it looks something like this. So you have, as I mentioned before, a Rabi flipping term, which drives between the ground and the Rydberg state on any given site. Then you have a laser detuning, delta, which you can think of as the chemical potential for the Rydberg state. And on top, you have these Rydberg-Rydberg interactions, which are represented by V. There are many equivalent formulations of this model. So for instance, you can think of this as a bosonic model by recognizing the ground state to be just a bosonic vacuum and the Rydberg state to be a state with one bosonic excitation. These are hardcore bosons. And unlike conventional bosonic models that you may be familiar with, the key feature here is that you don't have number conservation. So in the Bose-Hubbard model, for instance, your number is conserved. But here, because of this particular term, the number of bosons is not conserved. Okay. You can also think of it as a spin model. And in the spin language, this is nothing but a transverse field Ising model with long-range interactions and in a longitudinal field. Okay. So all of these ways of viewing the system, whether in terms of like the atomic degrees of freedom or bosonic or spin degrees of freedom, they're all equivalent. And depending on the context, it may be useful to think one way or the other. So now that I've introduced the many-body Hamiltonian, let's try to look a little bit into the quantum phases of this many-body Hamiltonian. Okay. So on this axis, oops, well, what just happened? No. Okay, good. All right. So on this axis, I'm plotting the interaction strength. And on this axis, I'm plotting the detuning over the Rabi frequency, so delta over omega. Okay. So when detuning is large and negative, all of the atoms just want to be in their atomic ground state. And when the detuning is large and positive, all of the atoms just want to be excited to the Rydberg state. However, you cannot do this freely. There's the interactions that we have to keep track of. And due to these interactions, the best possible configuration that the system can achieve is the Z2 ordered state, where you have nearest neighbor atoms blockaded. And so you end up with a state which is ground Rydberg, so on and so forth. Okay. Now, if the interactions are so strong that not only nearest neighbors, but next nearest neighbors are blockaded, you end up in the so-called Z3 state where you have Rydberg ground, ground, Rydberg ground, ground, and so on. And you can construct these Z4 orbit states. So then the question is, how do you actually prepare these states experimentally? Okay. The way to do that is you start off somewhere on the far left, what we call the disordered phase. There's really nothing disordered, it's just a name for the paramagnet. It's called a disordered phase. And in this disordered side, everything is in the ground state, atomic ground state, so it's easy to prepare. And then you ramp up this detuning and end up in one of these ordered phases. So this was actually carried out in these pioneering experiments from Misha's group in 2017. So this is a picture from this paper which shows the preparation of the Z2 state as we sweep the detuning from negative to positive. And similarly, these Z3 ordered states and Z4 ordered states, they were all prepared back in 2017. Yeah, please.
The interaction term here, are you increasing both the range and the strength?
Yeah, so
the one over R.
that's right. Yeah. So this should, okay, we conflated two things. So it should be interaction strength or blockade range, you can think. Those two are equivalent. The interaction is still 1 over R to the 6th.
And just some coefficient of 1 over R.
That's right. That's what's changing, exactly.
Why does it get so, I mean, is it like, I don't know what the scale is in the y-axis, but I thought of this 1 over R6 as just really blockading things outside of a certain radius.
That's right.
And so as you keep increasing the strength though, the radius grows?
That's exactly the right. Yeah. So as you increase the interaction strength, it
It just takes you have to increase it significantly to go from
that's why you have extended phases in the world.
It's such a rapidly dropping thing. You have
Exactly. So I don't know if I have the definition of the blockade radius in the previous slide, but essentially, it's V over R to the RB to the power 6th is equal to omega. That's the condition which defines the blockade radius. Okay. So it goes as like V to the 1 over 6th. Yes. So that's, yeah. So you really have to increase V significantly in order to blockade one other atom. Yeah. Great. Yeah, please do ask me any questions that you have in the meantime. I want this to be interactive. All right. So these phases, if you think about it, they're kind of boring. They're classical in the sense that they're just simple density wave orders. But what's interesting is rather the phase transitions between them. So again, many of you probably know about quantum phase transitions, but just to bring everybody on board, I want to give one slide overview on quantum phase transitions, and particularly second order or continuous quantum phase transitions. So a continuous quantum phase transition can be thought of as an avoided energy crossing. So I vary some parameter in my Hamiltonian, let me call it F. And as we do so, there is some gap in the system, which is vanishing at an avoided crossing. And the nice thing is that this is characterized by a certain set of critical exponents which are universal. So at a second order quantum phase transition, the gap of the system, the energy scale, it vanishes as we approach the quantum critical point with an exponent which is Z, the dynamical exponent, times nu, which is called the correlation length exponent. And similarly, as I approach the quantum critical point, my correlation length also diverges, and it diverges with this characteristic exponent mu. And the reason we are interested in these exponents is because of universality, okay? We have 50 years of renormalization group technology to actually calculate these exponents very well. And once we know these exponents, that essentially characterizes the full behavior of the system in the vicinity of the quantum critical point, irrespective of microscopic details. So we can treat many systems with one broad sweep rather than going instance by instance. So then the next question is that, great, we have these exponents theoretically, how do we actually go about measuring them in experiments? So the way to do that experimentally is via the so-called quantum Kibble-Zurek mechanism. Let me explain that physics. So as we approach a quantum phase transition, suppose the critical point, I have a linear sweep which goes across the second order quantum phase transition. I'm tuning some parameter, for simplicity, let's say linearly. Now, as I approach the quantum critical point, my gap is vanishing, or in other words, the relaxation time of the system diverges. So initially, as I vary my parameters, the system just follows the changing parameters adiabatically. That's when we are in the so-called adiabatic regime. But as I'm approaching the quantum critical point, my relaxation time diverges. So the system can no longer keep up with the changes to the parameter, okay? And it falls out of equilibrium. So when the system falls out of equilibrium, it enters the so-called impulse regime. So Kibble and Zurek's idea was that once you're in this impulse regime, the dynamics are completely frozen. Their idea was that, well, the system cannot respond fast enough, so let's just approximate it by saying that the system does not respond at all. So you're frozen in this impulse regime. Now, what does this imply for the correlation length? Well, as I was approaching the quantum critical point, my correlation length was divergent. So what this also means is that since the dynamics are completely frozen in the impulse regime, they will be frozen until I cross the phase transition and come out on the other side when my gap again acquires a significant value. Then my dynamics unfreeze, okay? But because of this freezing, unfreezing picture, the implication is that whatever correlation length I froze in at this point is precisely the correlation length that I recover after I unfreeze, okay? So this correlation length actually you can calculate or estimate in some scaling form with the rate of the speed, and it goes as the velocity of the sweep to the power like minus nu over 1 plus nu z. And once you know this correlation length, you can sort of take the inverse of that to estimate the density of defects, which Kibble and Zurek were thinking about. But this in general is the summary of Kibble-Zurek physics, that you have an adiabatic regime followed by a regime where your dynamics are completely frozen and then they unfreeze again. So this Kibble-Zurek mechanism was actually tested experimentally in the Rydberg system for one of the phase transitions that we were collaborating on. So here in this picture, what I'm showing you is the correlation length as a function of the final detuning for different sweep speeds, okay? So I start off somewhere here and end up at a positive detuning, so I end up in some ordered phase, and you can see that the faster I go, the smaller my final correlation length is. In fact, we can plot this final correlation length as a function of this inverse detuning sweep rate, and you see that this is on a log-log scale, sorry, 1 log scale. And you can see very nicely that this agrees with the exponent that we expect from the Kibble-Zurek combination. And using this, we can calculate the value of nu, what we call nu over 1 plus nu z. And this also, from experimental data, we were able to show pretty good agreement between the theoretically expected critical exponents and what you measure based on the Kibble-Zurek mechanism in experiments. Please. Yeah.
What's the repeating talk about that? On one side, we take transmitting your person.
Yeah. This sort of a picture does not apply, but you can still think about going through the phase transition and write down a series of successive Landau-Zeno transitions to describe the dynamic. Okay.
So on the other side, there's still some mechanism to count how many defects there is.
Exactly, there is. Yeah, there is. Okay, great. So the Kibble-Zurek mechanism that I just showed you the data was in 1 dimension, but now, over the last couple of years, we have this technology to make 2-dimensional arrays of these Rydberg systems. You can make whatever geometry you want, square, honeycomb, Kagome, and you can even make an atomic Mario lattice if you are interested in having some fun in the lab. Okay. All right, so the simplest place to So the simplest geometry to actually study some of the interesting physics is unfortunately not the Mario lattice, but perhaps the square. So in the square lattice, what does the phase diagram look like? So once again, I'm plotting on the y-axis the blockade radius, and on the x-axis the detuning. We have the disordered phase on one side. And it's unsurprising that the simplest possible ordered phase is actually a checkerboard, okay? So this was the theoretical phase diagram that we calculated, and this is the experimental data. This checkerboard pattern has on a square lattice, you have 2 sublattices. The checkerboard, or what we call a nail order state, is simply one of the sublattices being excited to the Rydberg and the other being in the ground state. So this is data on a 256 qubit Rydberg atom array. And you can see really beautifully the agreement between the theory and the experiment in mapping out this checkerboard lobe. The full phase diagram of this problem is rather complicated. It has many complex ordered phases. I don't want to get into the details of these ordered phases, but I just wanted to show you this phase diagram so that it could convey how beautifully rich all of this is. So for the rest of this talk, what I'm going to be focusing on is this phase transition from this disordered state to the checkerboard state. Now, this phase transition actually belongs in the universality class of the 2+1D Ising quantum phase transition. We understand its critical exponents pretty well. So naturally, the question was that can you study and measure these critical exponents using Kibble-Zurek type physics? Yeah. Yeah.
Theoretical predictions, we've got the star phase.
Yes.
I said, shouldn't it be in the experiment? Or-
Yeah, this
Or
is
or you're just
this is
measuring-
star phase.
You're just measuring different things.
Yeah, we just measure, yeah. So these are like individual order parameters that are designed for the different phases and they have some overlap, so you plot them differently. Yeah. Right. So then the natural question is, again, can we look at the dynamics across the phase transition in this two-dimensional setting? We did look at this data a few years ago, and there was some things that didn't quite sit right. And over the last few years, many people have also realized this, that the Kibble-Zurek mechanism is actually only an approximation. And in reality, there can be significant physics beyond it because the system does not actually freeze as you're going through quantum phase transition. Okay. Instead, there's actually a non-equilibrium correlation length that continues to grow with time, even as you're passing through this phase transition. So this has been realized by many people, including like Zurek himself in this paper. However, all of the work that had been done to this point was sort of instance specific. Okay. What I mean by that is if you have, say, a 1+1 Ising model that you can solve exactly, you can write down the dynamics for a phase transition. You can write down like an ON model with n going to infinity, and then again, you recover some exact emergent integrability that allows you to solve, address these dynamics. However, what we wanted to do was develop a formalism which is completely model agnostic, okay, does not rely on too many of the microscopic details of what problem you're solving, and can address both the Kibble-Zurek physics and the physics beyond it, which we call coarsening. So coarsening is actually a rather old subject in classical physics, which goes by the name of phase ordering kinetics. So the basic idea is that systems quenched from a disordered phase to an ordered phase do not order instantaneously. Instead, the length scale of ordered regions continue to grow with time as different patches of symmetry breaking order compete to select the ground state. Okay. So here, for instance, is a completely classical simulation of an Ising model, okay, which has been quenched from a high temperature state to the ordered state. And here, as a function of time, I'm showing the dynamical evolution of the system from the initial disordered state to the final ordered state. As the time goes on, a few features become immediately clear. You can see that, well, initially so it's an Ising model. You can have spin up, spin down. So there are two species, which I've marked in black and white. And you can see that as time goes on, the black tends to aggregate with black and white tends to aggregate with white. Okay. That's what we call coarsening. Okay. The other feature that perhaps is not as obvious is that the domain growth is a scaling phenomenon in the sense that the domains at later times look statistically self-similar to the domains at earlier times, apart from a global change in length scale. Okay. So if you look at some of these pictures and like zoom in into this region over here, that statistically looks like this region at later times. Okay. So the pictures that I showed previously, they were for the classical problem. And now we're going to try to extend this to the quantum problem and what happens. So I'm considering a completely general situation where on one axis I've plotted the tuning parameter of my system, which I call G. And let's say that there's a critical point, a quantum critical point located at GC equals 0. On the y-axis, I'm plotting the energy density of the system. Okay. Normally, when you see a phase diagram like this, you may be accustomed to seeing a phase diagram which is a tuning parameter and some temperature. However, here we're in a non-equilibrium situation, so it's more useful to think in terms of energy densities rather than temperatures. So generically, we're interested in a situation where the system starts in some easy to prepare disordered phase, and then we ramp some parameters and end up in some ordered phase. Okay. This is literally what you do in every analog simulator. This goes by the name of adiabatic quantum computation. Okay. So what does this ramp look like in this epsilon G plane? Well, you're starting off in the disordered phase. Now, if you follow the trajectory in this plane, at some point you fall out of equilibrium, so you heat up. So you no longer remain on this x-axis, but rather there is a finite, you go up along the y-axis, and eventually you end up somewhere in the ordered phase, okay? But you're heating up in this process, so you're actually going up in energy density. All right. So then, during this process, as the system is driven into the ordered phase, the long-range correlations of the ordered phase take time to develop. As I said, there are different competing patches. They don't agree with each other, so there are domain walls between them. So a natural question that you can ask is that how does long-range order develop as a function of time if it does develop at all? Okay. And to understand this, yeah, please. That's a great question. I'll show you later how conservation of energy can be satisfied. Okay. This is actually a very important part of the story. All right. So as I was saying, to understand this physics, there are three important length scales in the system that we need to think about. Okay. So firstly, there is a non-equilibrium correlation length. So if I stop the experiment at any point, just took a snapshot and measured what my correlation length is, this is the object that I'm measuring. This is the non-equilibrium correlation length. There's also the correlation length of the instantaneous ground state. Okay, so depending on where I am in G, I have a ground state of the Hamiltonian at that point. That ground state has a correlation length. So this is what we call psi quantum. Okay. Now, since we are out of equilibrium, L of t does not necessarily track psi quantum. Okay. The other thing is that because we have heated up above the ground state, there's also some thermal equilibrium correlation length. This is the correlation length that I would measure if I was sitting at some point in my phase diagram and I was in equilibrium and I measured the correlation length. Okay. But in general, all three of these are distinct from one another because I am not in equilibrium. Okay, great. So now that I've introduced these correlation lengths, we can work out the full dynamics as we are going through this quantum phase transition. Okay. So as the ramp proceeds, initially the system, the ground state will evolve adiabatically. It's building in the quantum correlations up to some short length scales. Okay, that's what this red dot implies, that we are in an adiabatic regime. And next, as the system passes through the quantum critical fan, it can undergo a small amount of what we call quantum critical coarsening. Okay. So what do we mean by that? What I mean by that is that in this region, in this quantum critical region, the non-equilibrium correlation length, very loosely speaking, it grows with time with an exponent which is 1 over z. And this z is the same dynamical critical exponent associated with the quantum critical point. Okay. So I had my quantum critical theory of this particular QCP, and that's what shows up over here. So in this particular case of the Ising phase transition, this growth is ballistic. Okay. So then as I go deeper into the ordered phase, I exit my quantum critical region and I cross over to a region of non-critical coarsening. Okay. Now, this non-critical coarsening, which occurs at late times, this is again another, but generically it's a power law growth of the non-equilibrium correlation length with time. But this exponent, which I call ZD here, now it's different. This exponent is 2. And what I want to stress here is that this ZD, this has got nothing to do with the exponent of the quantum critical point. Okay. Normally, when we think about like power law growths and universality, we are accustomed to thinking in the vicinity of a quantum critical point. But here, what I'm telling you is that we're deep in an ordered phase. We're far away from any quantum criticality, and there is a different growth law which has got nothing to do with the quantum critical point. Okay. The second point which I want to emphasize is that this is again in sharp distinction to what Kibble-Zurek predict. Kibble-Zurek says that once I froze in, that was it. I chose my correlation length, and for the rest of history, I'm going to stick to that correlation length. Whereas here, very explicitly, what we're showing is that no, that's not the case. This non-equilibrium correlation length has significant dynamics, which is not captured in this Kibble-Zurek picture. So far, like, yes, please.
Talked about when you go through a phase transformation condition, you get some classical phase transition, you get some coarsening.
Yes.
Are you ramping through a phase transition?
So there is a quantum phase transition which is
But
located
then
over
your
here.
path, your red path goes through that.
The yellow
The
region. Yeah.
yellow region.
Yeah.
right.
So you anticipated the next physics that I was going to highlight. Okay. So yeah, I was getting there. So what- as was anticipated here. So, I did assume that on the ordered side, there is an ordered phase that persists to some finite temperature or some finite energy density. And this, along this axis, there is a phase boundary, which I assume is critical, okay? Well, so in the vicinity, if I stop my ramp in the vicinity of this thermal phase boundary, okay, I can have a third scenario, which is an intermediate regime of classical critical coarsening between the quantum and the non-critical. Now, again, this classical critical coarsening is a third independent scenario because it's a growth law with a third exponent, which I label here by Z bar, okay? Again, for this particular problem, Z bar is known numerically to be like 2.16, and it has got nothing to do with the non-critical coarsening here. It's got nothing to do with the quantum critical coarsening here. Okay. But now, once I've introduced these three scenarios of quantum critical, classical critical, and non-critical, I can essentially describe this whole plane. Okay. For instance, suppose I have a ramp. Now, remember that a ramp is just some curve in this plane, and the dot implies where the ramp stops. Okay. Now, if I just stop my ramp directly on the thermal phase boundary in a very fine-tuned situation, this classical critical coarsening can go on forever. There can be another situation where, as I'm going through the phase transition, I went so fast that I did something very violent. I injected a lot of energy into the system that drives me out of the ordered phase altogether, okay? So then after some initial coarsening, the system realizes that it has to actually equilibrate to a disordered phase and not the ordered phase. Okay? And so then eventually at late times, the system will just equilibrate to the disordered phase, and depending on where you stop, there can be some period of classical critical coarsening or not. Now, this all looks very complicated. And why am I going through this? The reason why I'm introducing this formalism is because once these 5 cases are the only possible scenarios for any ramp that you can design. Okay, no matter how fast you go through a system, how slow you go through a system, whatever profile you use to cross the quantum phase transition, it has to fall into one of these 5 scenarios. Okay. And so if we can understand the physics of these individual scenarios one by one, we can piece them together to actually get the full picture of the non-equilibrium dynamics through the quantum phase transition. That's the idea. Okay. Yeah, please.
Fix something. What about like superuniverse and the same thing?
Yes, great question. So the quantum critical coarsening is governed by an exponent which is Z, and that cares about the dynamical exponent of the quantum critical point. Okay. The non-critical coarsening, okay, over here, that exponent is 2, and that cares about like what is the microscopic mechanism for the removal of domain walls. Okay. In this case, the mechanism is curvature driven, which gives you this 2. Okay. This thermal phase exponent, which is 2.16, we only know how to calculate that numerically, and it depends, that varies depending on what this thermal transition is.
Sorry, but it does depend on like the underlying conservation.
Of course, yes,
So
yes.
that's important.
Yeah, that's also important. Yeah. So it again depends on like what sort of conserved quantities you have also. Yeah.
Maybe I can get back to what I was confused about. With the red curve.
Yeah.
You're passing through the classical phase transition.
That's right. Yeah.
But that doesn't seem to affect.
It does.
That's what I guess I'm.
Yeah. So essentially, if you work out the details, what you can show is that for this red curve, you just don't spend enough time in the classical critical region to really feel the effects of the classical critical coarsening.
But then could, like, do a family of curves where you spend longer and longer in this classical field, you never let end up in the ordered phase.
Right. So the only way to really see the classical critical coarsening, and you can show this explicitly, is that you have to really stop in that region, in the vicinity of this term. So unless you stop, you will this can be worked out
Is
mathematically.
it for like a linear ramp, or like, I'm imagining if I could spend a really long time, like 6 days in there and then keep going over the ramp.
Well, then yeah, if you're spending 6 days, then you're effectively stopping in the classical critical region. Yeah.
So you just need some, so I'm thinking of some weird path,
Yeah,
where you just say, don't, just say.
this is just a linear ramp.
Simple linear ramps then, yeah.
Yeah, this is a simple linear or power or uniform ramp. And you can, of course, cook up some scenario where, very artificially you spend 6 days in the classical critical region. Sure, and you feel the effects of the classical critical course. But again, you have the information about what the dynamics is during each of these pieces. You have the information for what happens during that ramp. Okay. So the way you actually, this looks like a complicated problem, as you can guess. And the way you actually make some progress with this is by writing down universal scaling functions. I will spare you the pain of going through all 5 cases, but let me just consider the simplest case, which is that we consider a steady linear ramp without stopping. And we're going to consider what I call case 1 on the previous slide. Okay. So the scaling hypothesis just says that there exists at late times a single length scale, L of t, such that the domain structure is in a statistical sense independent of time if I rescale all lengths by L of t. Okay. So that's my scaling hypothesis. It's a hypothesis, but it, we numerically and we have a lot of good evidence that it works. Okay. Okay, sorry. I think I'm pressing the wrong button on this one. Okay. So what does the scaling hypothesis look like? So we have the non-equilibrium correlation length. We say that that is some number, which is the Kibble-Zurek length, times a function. Okay. Now this function is what encodes the universal information, and it's a function of one variable, which is the time divided by the Kibble-Zurek time. Okay. This scaling variable, let me call that x. Okay. Now, how does this function encompass all the information as we go through the quantum critical point? So when x is much smaller than 1, or my time is much less than the Kibble-Zurek time, I'm effectively in the adiabatic regime. Okay. When x is of order 1, I'm in my quantum critical regime, so the time is comparable to T Kibble-Zurek. And when x is much greater than 1, I'm in the non-critical coarsening regime. Okay. So this function essentially takes me from all 3 regimes that I encounter in case 1. So what does this function look like? Well, initially I'm going adiabatically. So this function actually follows the correlation length itself, and the equilibrium correlation length. So this goes as like x to the power minus mu. When x is of order 1, what happens is that because you've heated up, you really avoid the true quantum critical point. So there's no singularity in this function. This function in this region is smooth. It's some order 1 number that you cannot really calculate, but it's just order 1. What's interesting again is that you can show that at late times, this function is x to the power, this weird combination of exponents. And this exponent, if you just plug in the numbers for the 2 + 1d Ising quantum phase transition, you'll find that that exponent turns out to be like 0.186 or something like that. So it's a very small number. So in other words, the late time growth is actually quite slow, okay, for this particular case where you have an infinitely long ramp. So similarly, you can work out all the other cases, which I'll spare you the details of, but it's there in our paper. We showed how you can piece together the function from different regimes. The one thing which I just want to quickly mention without getting into any of the details is what happens when you stop the ramp. And this is a very practical question because in real life, you're never going to have an infinite ramp going forever. And as I showed previously, you really need to stop the ramp in order to have access to some physics like the classical critical coarsening. So the complication in the story that comes from stopping is that it introduces another time scale into the problem. So this is the stopping time. So now instead of having a 1-parameter universal scaling function, what we end up with is a 2-parameter universal scaling function with the arguments being t over tkz and t stopping over tkz. And in terms of this 2-parameter universal function, all regimes in the 5 scenarios that I showed before, they can be addressed. Okay, so all 5 regimes essentially corresponds to different corners of parameter space for this 2-parameter function. And the details are complicated, but if you're interested, you can find them in our paper. Okay. So this universal scaling function essentially gives you full information about what happens as you're going through this one critical point. Okay. So now, as I showed before, that the 5 scenarios of coarsening, They correspond to essentially different points where you end up in this G epsilon plane. So you have a ramp, that ramp took you somewhere and positioned you somewhere in this parameter space of some tuning parameter G, some energy density epsilon. Okay? And once you've decided where you end up, the coarsening follows depending on that point. Okay. So instead of going through a ramp, which is you fall out of equilibrium, it's rather violent and uncontrolled, you can actually study coarsening in a controlled setting by deterministically preparing a state with a certain energy density. Okay. How do you do that in the Rydberg setting? Well, in the Rydberg setting, the way you do it is you can seed some initial domain. Okay. So as I said before, the way you prepare these states, you start off with everything in the ground state and then you ramp up the detuning delta. But now what we do is on top, we add this light shift, which is this little delta, and this light shift actually pins certain atoms to specific configurations. Okay. So that's what we are showing in this picture. So you have a light shift that pins certain atoms, and this is a checkerboard phase with one type of antiferromagnetic ordering on the outside, and inside there's a different type of antiferromagnetic ordering. Okay. You can multiply everything by a factor of -1 to get this rather clean picture. So you can see that there's a sea of white type of antiferromagnetic ordering with an island of the gray type in between. Okay. And this island actually sets your energy density. Great. So then we can ask that, the physics of coarsening should also be visible in these seeded domains. And these are numerical simulations. I'll show you experimental data later on. So I initialize my system in one of these island-like states with a seeded domain. You can see that there is a big domain wall outside. And I start off at some initial detuning, which is 2, and then I let the system evolve. As time goes on, you can see that I seeded the system with this initial domain that vanishes. Okay? The domain melts away. So this is the physics of coarsening again, the big fish eating the small fish. Okay? It's probably a little easier to visualize if I just flip this slightly. So here I've just applied a staggering field. So it's the same picture. It's just multiplied with a staggered -1 factor. So you can see clearly that there's one domain on the outside and one domain on the inside. And again, as time goes on, this melts away. So this was for one particular value of the detuning, which is 2. But I can look at the same physics for different values of the detuning. And in particular, I'm showing you the dynamics at 4, which is deeper into the ordered phase. In this case, the critical point is somewhere around 1 to 1.5. So 2 is closer to the one critical point, 4 is deeper in the phase. And you can see that over the same time scale, the same size domain does not melt away, okay, over the same time scale. So the dynamics are actually much slower, deeper in the ordered phase. And the reason for this, again, is that there are different types of coarsening. Closer to the quantum critical point, you're dominated by the effects of quantum critical coarsening, which is ballistic and faster. Whereas further into the phase, you're actually dominated by non-critical coarsening, which is diffusive and slower. Okay? So this is a nice visualization of how the different types of coarsening come into play. So this is essentially the same figure, same data as I showed on the previous slides. Oh, I'm sorry, I keep on making this mistake with this clicker. This is essentially the same data that I showed on the previous slide. Essentially, I'm tracking the imbalance in the system, the perturbation in the system that I introduced by putting in this island as a function of time for different detunings. And you can see systematically that as I go to larger and larger detunings, the dynamics are slower, as I said, because of the relative influence of different types of coarsening. The other feature that I'd like to point out is that at 1.5, you can see that at late times, the imbalance actually grows as a function of time. And this is surprising at first sight because 1.5 is still inside the ordered phase. Remember, the quantum critical point is somewhere around 1. But what's happening here is that you started off not in the ground state, but you started off in the seeded state. So you started off at some finite energy density. So even though the ground state was ordered, at this particular energy density, the state was actually disordered. So the coarsening eventually takes the system to a disordered state. So what this tells you is that by then controlling the size of these individual domains and by controlling where you're sitting in parameter space, you can actually perform some sort of quantum thermometry to map out this thermal phase boundary systematically. Okay. So this coarsening dynamics can actually be useful as just a practical tool to get thermal information about the system. Okay. So in the last 15 minutes or so of my talk, I'll tell you about some experiments. I'll address the question of energy conservation. But before I go on to the experiments, let me just briefly summarize what our theoretical expectations are. So far, I've shown you that in the non-equilibrium dynamics across the phase transition, they should expect some coarsening physics, which really is far beyond this Kibble-Zurek description, okay? And this can actually be very important when you're trying to do quantum state preparation via adiabatic algorithms, okay? What this is telling you is that if you only have a finite amount of time that you can run your algorithm for, maybe it's better to budget your time schedule such that you have more time allotted for the hold period, where you're just not doing anything but letting the system evolve under its own dynamic, as opposed to like really going slowly through the quantum phase transition. Okay. All the dynamical scenarios that one can engineer and expect, they can all be encompassed by this 2-parameter universal scaling function. So you, in principle, have all information about the behavior through the phase transition. And these coarsening dynamics, they speed up as we approach the quantum critical point because they're different types of coarsening. All right. So with that theoretical background, let me in the next 15 minutes or so just tell you briefly about the experiments that we did. I should say that, when I say we did, we collaborated on the experiments. The experimentalists were doing these actual work. So again, once again, this is a 256 atom Rydberg array. You've seen these pictures before, but essentially this is what it looks like if you take a snapshot at some point. So you have some atoms in the ground state, you have some atoms in the Rydberg state, and then you let the system evolve. You take the system to some final point, some final detuning, and then what we do is we stop there, we hold the system for some finite time, and then watch the evolution as time goes on. So as I said before, there are two types of competing antiferromagnetic orders. So this is what we call AF1 and AF2, and I show that in white and gray over here. So now what does the dynamics look like during this hold period? So at early times, this is plotting the correlation map in real space. You can see that there's definitely some correlations, which is going to form the long-range orbit state. And visually, if I just take one instant representative snapshot, you can see some patches of gray, some patches of white. Then I let the dynamics go on for some time, and then I look at the same correlation map at a later time, and you can see that the correlations indeed do spread. And very visually also, if you look at this individual snapshots, you can see the bigger domains trying to eat up the smaller domains. So this is pictures, but you can also see this very quantitatively if I plot the correlation length as a function of time. So here is the correlation length on the y-axis plotted as a function of the hold time. And you can see that it does actually exhibit significant growth as time goes on. Not only does the correlation length grow, it grows in a very characteristic fashion. So if I plot psi squared, this is again the non-equilibrium correlation length, as a function of the hold time, you can see that at early times, this growth is actually linear, okay? And it is faster for delta equals 2. The slope, you can see, is larger for delta equals 2 than for delta equals 4. So this linear growth of psi squared versus t, which implies that psi grows as t to the 1/2, that is exactly what we would expect from non-critical coarsening. At late times, there are several decoherence mechanisms at play, so the data is not as nice, but at early times, at least, you see very clearly this growth. The other feature which we can try to squeeze out from this data is there any, I said that the scaling function is really universal. So can we see some of this universality in the experimental data? So what we look at here is not the data in real space, but rather in Fourier space. Okay, so we have some real space correlation map. We can Fourier transform that and look at the structure factor. And we look at the structure factor as a function of K. And then what you can show actually just from the bare experimental data is that you can rescale the structure factor and get beautiful data collapse as a function of a single scaling variable. And this is really a signature of self-similar dynamics or some dynamical universality that emerges in this problem, as we would expect. All right. So I've shown you that the correlation length grows. Great. That is what we would expect. But let's look at this a little more carefully by going real deep into the microscopics. Okay. So on this axis, on the first plot, I'm plotting the average occupation. I'm plotting as a function of the domain area. So what this is telling you is essentially a histogram of the distribution of domain sizes. Okay. And I'm plotting that for two different times, early times in blue and late times in red. And you can see that initially in the system, the distribution is peaked with around a domain size of like 125 atoms, whereas at a later time, you can see that the distribution actually shifts very significantly rightwards, which means that your domain, the largest domain in your system, has actually grown significantly by coarsening. In fact, this is exactly shown in the next plot, which plots the area of the largest domain and the area of the second largest domain in blue and red respectively. And you can see that as time goes on, the largest domain gets bigger and the second largest domain shrinks. And that is exactly what you'd expect if you have one domain eating up another. Okay. So remember, this was not just one domain. This was, you had a ramp through the quantum critical point. So you start off with many patches of competing domains. And from that, you end up in something which is peaked around, close to 200. The system size is 256, so you really have a macroscopic domain in the system. Microscopically, as these domains are growing, what's going on? How is energy conservation satisfied? So to do that, what we can look at is the total energy of the system as a function of the whole time. And we only have, from snapshot data, we only have access to the classical part of the energy, the ZZ terms, and not the X term. And we can divide this energy into two pieces, okay? There is some contribution to this energy cost, which comes from the domain walls, okay? And there's some contribution to the energy which comes from spin flips within a domain. So that's what we call the bulk and the domain wall contribution. And as time goes on, you can see that the total energy, that's relatively flat, whereas the bulk contribution to the energy goes up and the boundary contribution to the energy goes down. What this is telling you is that the domain walls are hot, the bulk of the interior of the domains is cold, and as time goes on, you have excitations being transferred from the domain wall to the bulk of the domains as single spin flips. So just like you learn in kindergarten about energy being conserved, there are different forms of energy, kinetic and potential, and they get interchanged between one another. This is just a grown-up version of that. There's a bulk energy and a domain wall energy. While the total is conserved, you just get a transfer from the domain walls to spin flip excitations inside the bulk. All right. Okay. So then, this is very neat, but we were not the first to do coarsening experiments. There have been lots of coarsening experiments in superfluid systems, for instance. And for those, essentially, you can, in a lot of those cases, write down a mean field-like description of the dynamics. So what we really wanted to show and claim was that this is really the first coarsening experiment where we can certify that the dynamics are really driven by quantum fluctuations. We have good reasons to expect that because we know that from the experimental data, we know that the dynamics are coherent up to quite late times. So we should expect this to be driven by quantum fluctuations. But how can we actually certify that? Okay. So to do that, we employ the trick that I showed you theoretically before. So we look at the dynamics at different values of delta, and we ask, how over some period of time, do I see the dynamics accelerate or decelerate as we approach the quantum critical point? Okay. And in fact, like if the dynamics were driven by thermal fluctuations near a thermal phase boundary, they should get slower as you approach that phase boundary because the Z bar exponent is larger. Whereas in this case, as you would expect, you see that the dynamics do accelerate as you get closer to the quantum critical point. And this is really telling you that these dynamics are driven by quantum rather than thermal fluctuations. Again, these are pictures, but you can look at this data more quantitatively. You can look at this data more quantitatively. So here on the y-axis, I'm plotting the area of the largest domain, which is r squared. And I'm looking at that area as a function of time for different values of delta. And you can see that it does shrink. And the rate at which it shrinks is faster the closer I am to the quantum critical point. In fact, like you can say, go a little bit beyond that and look at the rate, the d area over time, the rate of change of the area with time. as a function of the distance to the quantum critical point. Okay. And we only have a few points of data because we were limited in what detunings we can access experimentally. But the theory actually makes a pretty concrete prediction, which is that the dependence of this rate of shrinking at early times, it should depend on the distance to the quantum critical point raised to this power of minus nu, again, which is a quantum correlation length exponent. And you can roughly see that it is linear at early times with this exponent. The second piece of information that you can look at is that, well, macroscopically, I do see this domain shrinking, but are the dynamics really coming from the boundary as this domain shrinks, or is there some perturbations going on in the background that's masking my signatures to make me falsely believe that there is some shrinking going on? So to do that, what we looked at was the dynamics layer by layer in the system. So here is, I look at the dynamics at a central point and at the diamond, which is 2 sites away. And then I look at the dynamics for this patch, which is this ring, which is 8 sites away. And you can see again that there are significant dynamics going on in the vicinity of this domain wall boundary, whereas if I look deeper into the bulk in this ring, it's flat as a function of time. All right. So by now we have characterized the dynamics microscopically very well. We have a lot of good data, both theoretically and experimentally, to show that the coarsening physics has significant effects on the system. The last thing we want to characterize is what happens microscopically to drive the coarsening. Okay. And we have a theoretical understanding of that, which we want to test experimentally. The theoretical understanding is that the excess energy is localized in the domain walls. So coarsening occurs by a reduction in the radius of curvature of these domain walls. Okay. So coarsening essentially wants to straighten out or flatten these domain walls as a function of time. Okay. So to test this physics, what we again looked at was a seeded domain where we initialize the system in the zigzag pattern. Okay. The reason we chose this pattern, and we predicted this theoretically, is that there are regions of high curvature and at these corners, whereas in between them, there's a flat region with very little curvature. So in the same system, just by seeding it with this particular configuration, we can test the influence of the local radius of curvature on the coarsening dynamics. And you can track the evolution as a function of time, and you can see how these sharp edges melt away as time goes on. Let's look at this quantitatively. So I'm plotting the local order parameter as a function of the horizontal distance. And what I mean by that is I'm going to be taking cuts across this system and looking at the dynamics through these cuts as a function of time. So these red and blue cuts are at regions of high local curvature, whereas the green and yellow are at regions of very little curvature, none actually. Lighter colors means early times, and darker colors means late times. And you can see that for the blue and the red curves, as time goes on, the blue curves move rightwards and the red curves move leftwards. In other words, the system is trying to get rid of the curvature at the corners and flatten that out. So this domain is moving here, and this domain is over there. Whereas on the other hand, if I look at the green and the yellow curves as a function of time, there's very little dynamics. They roughly stay where they were to begin with. So in the region of low curvature, there is no dynamics. And this is consistent with the fact that we can write down some effective theory for what drives the coarsening, and you can show that this is consistent with that. A very striking example, which is a more extreme case than this, is that you can prepare a state with exactly one straight domain wall. And here I'm showing the dynamics to a time, which is 0.7 microseconds, and that's actually larger than what we had over here. So this is a longer time than 0.45 microseconds over here. And despite the fact that we are going down to a larger time, you can see that this configuration remains pinned. There are some dynamics which goes on near this phase boundary that smears out a little bit, but we can look at this again, staggered magnetization as a function of the site index, and it doesn't really move much as a function of time. So in the system where you have high curvature points, the coarsening has significant effects, whereas if you really remove the curvature from the system, you can get the coarsening. Okay, So with that combination of theory and experiments, so hopefully I've given you some flavor of how quantum many-body dynamics can be used to probe universal physics. As I said before, like normally when we're accustomed to thinking about universality in the vicinity of some quantum critical point, and here we can have emergent universality that's just as universal, but has nothing to do with quantum criticality. Then I hopefully showed you that this non-equilibrium dynamics across the quantum phase transition, they do involve some Kibble-Zurek physics, but they involve a very important correction beyond that, which is this coarsening. There can be multiple types of coarsening phenomena depending on what ramp you choose, what protocol you choose, but don't worry, all possible coarsening phenomena can be encompassed by this two-parameter universal scaling function. And while what I showed you today was for an analog quantum simulator where we really had a microscopic Rydberg Hamiltonian, we were studying the dynamics. Recently, Google looked at some of these dynamics in a hybrid system where they had both hybrid analog and digital dynamics in superconducting qubits. And in this recent paper, they were actually able to verify many of our predictions and show beautiful data collapse, which really verifies the universality and self-similar dynamics of this theory. So with that, and thank you for your attention. I'm happy to take any questions.
Which one of the coordinates is driven by the curvature? Or
That's a great question. So you're asking which coarsening is driven by the curvature, and that's the non-critical coarsening part. Yeah. That's what gives rise to the exponent of 2.
So, what is quantum about this quantum?
Great question. Yeah. So, okay. So the dynamics are all intrinsically.
Phrase it also, like I feel like a lot of your pictures are fairly classic. You're just looking at this quarter parameter and whether you were talking about a quantum system or a classical system, there were different time scales, but that's about, as far as I can tell in your presentation. That was like the quantum case just made the time scales more complicated.
Mhm.
But I didn't see if there was some, like, you're able to do this on some quantum computer and have access to the full quantum state. I wonder if there's something intrinsically quantum happening in this quantum course.
That's a great question. So the quantum part is that all of the microscopic dynamics that's going on that is driven by quantum mechanics. Okay. So you have these domains expanding and shrinking. Okay. At the Hamiltonian level, what is driving the shrinking and expansion of domains? It is the sigma x term. It's a transverse field that's driving these dynamics. Okay. So really the dynamics are driven by the quantum mechanics of the system. Now, to address your question, it is true that in the quantum, you will probably agree without a doubt that in the vicinity of the quantum critical point where I have the quantum critical coarsening, that really is a phenomenon associated with the quantum critical point. Okay, there is no classical analog of that at all. Okay. It is driven by quantum fluctuations. It has got everything to do with the quantum criticality, and that shows up in the fact that you extract an exponent off a quantum critical point, the z of the quantum critical point in your dynamics. Okay. Now you may ask, what about the non-critical coarsening? There I have this theory of curvature-driven coarsening, and that seems classical. And you're right, that it is an underlying theory where the dynamics are quantum, but we can write an effective renormalized classical description for it, which looks like a theory where the dynamics are just driven by domain wall curvature. Okay. So the effective theory for the quantum dynamics deep in this ordered phase is just the same as the dynamics of a bubble driven by surface tension. But even though the renormalized theory looks classical, you have to remember that what is driving that microscopically is the transverse field in the Ising model.
Maybe there's another way of phrasing it, like maybe even the notion that you're in one domain or the other is
Yeah.
classical. And that quantum mechanically you might be in both.
Exactly. Absolutely. Yeah.
That play a role.
Absolutely. So let's take a look at these pictures, okay? So for instance, here, this is plotting the expectation value of sigma z or sigma x on any given site, okay? And you can see that even though I look at the expectation value, I can see that this domain gets eaten up. Okay. Now, if I look at like my experimental pictures, okay, I take a snapshot. What do I see? I don't see anything which looks as beautifully ordered as I showed before, right? Experimentally, you see, one domain which looks like this, something which looks like that. So you experimentally, if you take a snapshot, you will see you will see many different domain configurations. So your state in the experiment or the state at any given point of time is a superposition of many different domain wall configurations. Okay. If you look at the expectation value averaged over all of this, you get something which is very nice and symmetric and looks like this. Okay. But if you take the snapshot at any given point in time, it looks completely disordered. So although this is what you're seeing at the expectation value level, microscopically, this is coming from a superposition of many, many quantum states. So this is really not classical. Exactly. So that's a good way of thinking about it. So to reframe the question, you're saying, what happens to the superposition as a function of time? What's happening in the superposition is that you have different domain wall configurations and they have different weights. And as time goes on, there's a reweighting of these different configurations in the superposition. So what's happening is that the weights of the configurations where I have fewer domain walls or I have larger domains, that increases as a function of time, whereas the smaller ones shrink. Okay? So as time, even though these dynamics may look classical, at the microscopic level, what's happening is a reweighting of the different coefficients in the superposition. And you seem unhappy, but I'm happy to like tell you if you have a concern, I'm happy to address it.
I think it's like if you deliberately couple the system to noise.
Yes.
Like, it sabotage the, coherence between different domain wall configuration while keeping the whatever probability.
That's right.
So is it just the probability is driven driving like the non-critical coarsening, or is it that the coherence superposition that is still playing a really good role?
No, the coherent superposition is important. Like if you just decohere the system, you wouldn't see this physics. So the coherence is important here. Absolutely, yes. So the fact that you have a coherent superposition, and while keeping that coherence, you have the reweighting between different configurations in the superposition is absolutely critical to this dynamics.
This one doesn't have a classical analog.
This does not have a classical analog. You can try to write down some sort of mean field equations to see if you can model the dynamics, and you can do such an exercise and you'll fail miserably. So
Maybe, and then on that note, maybe we can end the official part of the thing here. So next time, Brian, when you're.